So this is a problem from H.C. Verma, chapter Circular Motion, problem number 24. So the question is like so. We have been given a hemispherical bowl. Say this is our hemispherical bowl, and say this is the axis of the bowl, and a block is placed somewhere here. The mass of the block says m, with this angle being theta. So before I proceed with the rest of the question, let me just say that since the mass of this block is m, its weight is mg, and we can easily see that if we extend this line, this angle is also theta, and if we resolve mg along this direction, we get mg cos theta, and along this direction we get mg sin theta. So the question they are asking is this. They are saying, let us rotate this bowl around this axis at an angular velocity of omega. There is friction on the surface of this bowl. So there is friction between the block and the bowl, and the coefficient of friction is mu. So they are asking the limit of omega within which the block will not slip over the bowl. So we can say, first of all, we can easily see that the block also rotates with the bowl around this circle, and if the radius of the hemispherical bowl is r, the block rotates along a circular path with radius equals to r sin theta, which we can easily see from this right angled triangle. So a centrifugal force acts on the bowl, that centrifugal force being m r omega squared, where r is just capital R sin theta. Since there is friction between the block and the bowl, the friction can actually act in either direction, along this direction tangential to the bowl, or upwards tangential to the bowl, depending on in which direction the block is trying to slide. If the block tries to slide tangentially down, then friction will act tangentially up, and if the block tries to slide tangentially up, when will the block try to slide tangentially up? When the omega is too high. When the omega is too low, the block will not remain in its place and it will try to slide tangentially down, and that is when friction will try to prevent it by acting tangentially up. If the omega is too high, then the block will try to slide tangentially up, and friction will act in the tangentially downwards direction to prevent that motion. So first of all, let us see that this angle is 90 minus theta. So if I resolve the centrifugal force along this line, that is along this line, I'll get the sine component, just because this is 90 minus theta, and along this direction I'll get the cos component. You can also say that this angle is theta, because this is 90 minus theta and this whole angle is 90 degree. If I resolve the centrifugal force along this direction, I'll get the cos component, along this direction I'll get the sine component. We can easily see what the normal reaction is. Normal reaction is the force which acts normal to the surface of contact. So in this direction the normal reaction is acting. The normal reaction is the sum of this and this. So the normal reaction is just mg cos theta plus fc sin theta. So first of all, let us take the first case being the block tries to slide in the downward direction. That is when omega is not enough to sustain the circular motion of the block. So in that case, since the block is trying to slide in this direction, friction will act in that direction. So our equation for equilibrium condition of the block is mg sine theta equals to fc cos theta plus the frictional force. Frictional force is just mu times normal reaction being this. So normal reaction is mg cos theta plus fc sine theta, where fc is mr omega squared. So it's just mr omega squared sine theta. So mg sine theta equals to fc cos theta plus frictional force mu times normal reaction. Mu times normal reaction is this. I've just substituted the expression for the centrifugal force, although we still have to substitute the expression for small r, which is capital R sine theta. So if I move one step ahead, I get mg sine theta equals to centrifugal force. Again, centrifugal force is mr omega squared, where small r is capital R sine theta. So m capital R sine theta omega squared, and then we have a cos theta. This is just our fc, plus mu times normal reaction. Normal reaction is mg cos theta plus m, for small r will substitute capital R sine theta. So we get capital R sine squared theta omega squared So for small r we have substituted capital R sine theta. There was already a sine theta from before, so we get sine squared theta, and we carry over the omega squared. So if we isolate omega squared, we get mg sine theta minus mu mg cos theta equals to omega squared. From this term and this term, after multiplying this out, I get an omega squared will be common, mr will be common, a sine theta will be common. So I'm left with a cos theta, and I'm left with a mu sine theta. So m's will cancel out from both sides, and if I jump ahead, I can say that omega is g sine theta minus mu cos theta divided by r sine theta cos theta plus mu sine theta all over root. So this is the first case. This is when the expression for omega is not enough to sustain the circular motion. Of the block. I'll just check the answer if I've got it right. Yeah, I think I've got it right. Yeah. So let us now move on to the second case. I'll draw the diagram one more time. So here is our hemispherical bowl. Here is our block. The radius of the bowl is r. This angle is theta. The mass of the block is m, so the weight is mg. If I resolve mg, I get mg cos theta in this direction and mg sine theta in that direction. The block rotates in a circular path like so, in a circle of radius capital R sine theta, which we can find from this right angled triangle using simple trigonometry. A centrifugal force acts on the block, the centrifugal force being mr sine theta omega squared. Okay, if I resolve Fc, I'll find that the cos component acts in that direction, so this is Fc cos theta, and along this direction I'll get Fc sine theta. The normal reaction acts like so, normal reaction being mg cos theta plus Fc sine theta. And in our second case, if the value of omega is too high, the block will try to slide upwards and therefore friction will act in the downward direction. So our equation for equilibrium will be Fc cos theta equals mg sine theta plus frictional force, which is just mu times normal reaction being this mg cos theta plus Fc sine theta. We'll substitute the expression for Fc. Fc is just mr sine theta omega squared. There's a cos theta 2, mg sine theta plus mu times mg cos theta plus Fc sine theta. Fc is just mr sine theta omega squared, so we get mr omega squared sine squared theta. Let us bring all the omega squared to the same side. We have omega squared mr sine theta. We get a cos theta left over from this term, and if we multiply this out and bring this term to this side and take mr omega squared sine theta common, I think we get minus mu sine theta. Yeah. And what we are left with on this side is we get the mg common, we get sine theta plus mu cos theta. The m's will cancel out and omega will be g sine theta plus mu cos theta divided by r sine theta cos theta minus mu sine theta all over root. Let me just check if I got this one right. The numerator seems right. Yeah, the denominator is also right, so no problems with this. So we'll end this video here.